Hello and welcome to PHP North East. Thank you to our sponsors, Ronald James and I Am Property. If you're looking for a new development role, be sure to check those out. And for this month's talk, we have Rob Waller talking about how to handle code complexity. So Rob, I'll hand straight over to you.
Right, hello, good evening. Thanks for joining me. If there are any problems with the sound, please do let me know in the chat, because I am just going to start talking. I can't tell if there are issues with the chat. So tonight's talk is on code complexity. And how you handle it, the best strategies to handle it. Before I dive into the talk, I will give a brief summary of who I am. So I am Rob. I live in Aylesbury, which is UK, just outside of London. No one ever seems to know where it is, but it's near Oxford and Milton Keynes. Over the years, I've been developing for about 15 years. I've held the role of just a run-of-the-mill developer. I've also been a manager, and I've taken on the role of architect. I've coded in various languages, mainly PHP for the last 10 years, and also more recently looked into things like Node and Deno and Rust, which are enjoyable languages. And I do a fair bit of open source development. I have a library in PHP for JSON Web Tokens, which is relatively popular. And I've got a couple of things for Deno. On a personal level, I have now one baby who is approaching 1 year old, which is great, and two cats. One of the cats is not with me, thankfully. Otherwise, I'd be jumping all across the screen. And yeah, so let's dive in. So the start of this talk is about a subject called complexity theory. And complexity theory is a vast subject and deals with all sorts of issues. And there are parts to complexity theory that are useful in software development or apply to software development. Complex systems, which is the main part of complexity theory, are things like the World Wide Web or the internet, the immune system, and even the brain. And it's understanding how these systems work, these vastly complex systems work, and developing theories and ideas about how they work. It's a very new and early field, even though it's been around probably for 30 or 40 years. It's still relatively young. So some of the ideas are not necessarily settled on. But some of the useful ideas that apply to coding are as follows. The first one is the idea of emergence. Emergence is this idea of how complex properties emerge from very simple things. So on a very basic level, a good example of this is the properties of wetness and dampness. So basically, from a collection of water molecules interacting with an object, you will eventually get these properties called wetness or dampness. But this will depend on the object that's being interacted with and how many water molecules there are. And there's a fuzziness about this concept of emergence. Like, when does something become damp and when does it become wet? We know when it is wet, but we don't know at the exact point that it moves from being, say, dry to wet, say a solid surface. And different surfaces work in different ways. So a jumper might become damp, but a worktop will not become damp, it will just become wet. And this is the idea of emergence. And this obviously deals with much bigger ideas as well. So one of the concepts is consciousness, which is really hard problem to solve, is why does consciousness seem to emerge from the interaction of a vast number of simple neurons? How does that happen? What makes that happen? Currently, there are ideas, but we don't know. But there's this idea of emergence of complex properties coming out of very simple things. The next idea that's useful to us is the concept of tipping points. So with complex systems, what will happen is you will get these things called tipping points. And this is where state changes from one thing to another. And this state change is, in most cases, irreversible, or it's very hard to reverse or stop. Like, once you're moving towards a tipping point, it can be very difficult to reverse. Good examples of this, or a very simple example of this to begin with, would be an ice cube. Once an ice cube melts, you can never reform the ice cube into its previous state. It's tipped over into water. Even if you collected up all the same water molecules again and refroze them, you wouldn't have the same ice cube again, because the tipping point has been crossed. And you see this in other areas, much more complex areas, like forest fires, for instance, or economic crashes. Once you've tipped over, you've had an economic crash, it's never the same again. And this year, obviously, with COVID-19, we've probably crossed the tipping point. Society in the future is going to be very different to what it was previously. Just think about how many of us are working from home, and many of us will continue to work from home even when it's safe for us to go back into an office environment. The office environment won't be the same as it was previously. We've crossed the boundary, we've tipped over. There's been a fundamental state change. So these are two really interesting ideas that apply to code. And we have this idea in code of code complexity. And basically, complexity itself is an emergent property of software development. So as you code and as you develop, complexity can grow or will grow in your project. And the question is how do you handle this? And this can become a problem. So slowly, as complexity emerges, you can sometimes hit a tipping point where complexity becomes so great, the project goes from being very simple and easy to work with to very complex and very hard to work with. And the question is, how do we handle this? How do we handle this complexity developing in our software and try and keep it under control, right? Especially given as a product becomes more successful, more requirements get fed in, etc., etc. So complexity often grows naturally in software. Now, when we talk about code complexity, we're not talking about everything. We're not talking about all the things, okay? Because software, if you try and think about it as in its whole and in its entirety, is a vast subject. There's no way any developer could handle thinking about this on the whole subject of software, right? If you think about what it takes to run, say, something like PHP or JavaScript, there's a whole bunch of other software and stuff that needs to work to make PHP and JavaScript, your JavaScript code, run. But we don't worry about that when we're talking about complexity. Really, when we're talking about code complexity, we're talking about individual projects and individual code bases. Sadly, as humans, we're probably not capable of thinking, much beyond that, because code bases themselves can be pretty complex. So we're talking about code complexity within a singular code base or a singular project. Complexity or code complexity is not something that you can avoid. It will happen, as mentioned. As projects grow, complexity will grow. It's not something you can't just hide in a box and pretend it doesn't exist, right? Your only strategy with code complexity is to try and minimize it, to try and understand it and minimize the amount of complexity you have in your code base. Now, many of us will have worked at many companies that basically ignore complexity and just kick it down the road. Now, if you do that, there will be consequences. And what will happen is you will often tip over into what could be described as a complexity hole. And this works in a similar way to a black hole. Essentially, complexity grows to the point that you cross a sort of like event horizon moment in your software. And once you've crossed that point, your software is so complex and so difficult to use that in reality, you will often have to just do a rewrite. You won't be able to fix the problem. It will become unworkable. And if you've worked in software development as long as I have, 15 years now, you'll have seen a number of these types of projects where complexity has grown to such a point that it becomes almost impossible to work on. Now, complexity doesn't need to get to that point, right? You don't need to cross this idea, this sort of theoretical concept of an event horizon for you to have problems. As complexity grows and as you get closer to the black hole as such, you'll notice problems. And these are real problems that will cause you and your business issues if you don't handle complexity. The most obvious one is money. As complexity grows in a code base, your costs will go up, right? Because you will need more developers to solve the problems you have in a more complex code base or on a more complex project. So your costs will go up. You'll need to do more testing, right? You'll either need to do more testing or you'll need to fix more bugs in production. So that will increase your costs, particularly if you go for the fix the bugs in production route. That can be very problematic, and there's lots of stats and data showing that basically if you leave bugs to get to production, your cost of fixing a bug grows enormously. And then there's other costs associated with that. For instance, just getting adding new features and various other things. The second part of this, which is kind of connected to the money, is developer well-being, right? No developer wants to work on a super complex project, right? It's not fun. You don't learn anything, and it's just hard work. It's a slog, and instead of you enjoying development and enjoying adding new features to a product and feeling like you're giving that business value back to your customers and to your employer, you feel often that you're just keeping a house of cards upright, and that creates a lot of tension and fear and worry and stress, and that's not a good place to be in. And if you don't have good developer, you don't have developer well-being, you will get staff turnover, right? And then you get more costs. So you'll have more costs in terms of hiring new people, onboarding new people, getting them up to speed, and lots of problems there, right? Getting people involved in a new project that's very complicated takes more time than a project that's pretty simple or at least understandable. So you need to think about complexity because it will have real world impacts. It will cost you money, and it will affect the well-being of your development team and the wider team, project managers, product owners, everyone involved, everyone who wants to add value for users will have problems if you have a complex code base. So the question comes up is how do we handle this? So we can't avoid it. but we can minimize it. So how do we begin to start solving this problem? And the first step is how to spot complexity. And there are a couple of points to this. The first is metrics, right? So you need to be collecting some metrics. You need to be using some tools, and then you need to get good at code analysis. And when I say code analysis, I mean like manual code analysis, not running a static analyze or something like that. But we'll go through this. So there are three core metrics. Probably the most famous metric to do with code complexity is cyclomatic complexity. And this is the metric you'll have seen in most places. Most tools have this metric. And basically what it means is it tells you how many control structures exist in a unit of code. And a unit of code normally being just a method, right? Or it can be a class, but it will normally be a method that you'll assess this against. And if you've got an if statement and a for each statement, you'll get a score of 3. You get a point for the method signature. You get a point for each control structure. So if you've got an if and a for each, you'll have a score of 3 basically. And as this grows, as you get past 5 on a complexity score and beyond 10, you can see that your method will be beginning to get problematic. It will have a lot of complexity into it. The next metric that is useful is end-path complexity. And end-path complexity is slightly more complex, but it's also quite fun and it can be quite scary. Basically, end-path complexity tells you about the number of possible or theoretical paths there are through your code. And this grows exponentially, right? So as you get more and more decision points, so if do this, do that, if this, do that, whatever, right? As that grows, your end-path complexity will grow exponentially. And this can get very complicated when you've got loops in there as well. I've seen scores for end-path complexity for a singular method that have been in the billions. So if you really want to drive home the point to management that code is too complex, often show them end-path complexity, because quite simply the scores will be enormous. The final metric, which is useful, but probably the least well known, is CRAP scores. So CRAP scores are basically a merger of code coverage with complexity. And they give you an idea of whether, given how complex your code is, whether you have enough tests. Okay, so the more complex the code is, the more tests you'll need, because you'll have more paths through the code that need to be tested, essentially. So if you can keep your CRAP scores low, it means that you've got well-covered code, basically. CRAP scores you'll find in PHP unit, which I'll talk about in a moment. So these are the three core metrics. Cyclomatic complexity is the one you'll probably use the most and you'll see the most, but there are others that can also be useful. And there are loads and loads of tools. Pretty much every language that you can imagine has a tool that will run your cyclomatic complexity, your end-path complexity, and give you those scores so that you can assess your code. So in PHP, there's a really great tool called PHP-MD, which has been around for a long time now. And then in JavaScript, there's ESLint. ESLint has a bunch of complexity checks. One thing to be aware of, with a slight difference between these two tools, is their defaults. So PHP-MD sets the default for cyclomatic complexity at 10. 10 is still relatively high, right? So if you've got a cyclomatic complexity score, you've got a lot of methods that have complexity score above 10, you have a problematic code base. Really, you should be aiming for a score of somewhere between 4 and 7 is a good average score. Most methods, if you're following single responsibility, you'll have a score of 1 or 2 or something like that. So 10 is great if you're applying this to an existing project. If you're starting a new project, you start at 5. ESLint is a bit more liberal. ESLint, I believe the default is at 20, or at least it was last time I checked. 20 is very high. If you've got a lot of methods breaching 20, you've got a real problem on your hands with complexity. You're gonna have a real tough time, and basically you're gonna have a tough time testing your code. So if you're using ESLint complexity scores, just have a quick check of the defaults and make sure they're not above, they're set to about 10, somewhere between 5 and 10. Okay, but if you're using something like Python, there's also tools like I believe it's Radon can do the same thing. There's loads of tools out there. So if you're not using PHP or JavaScript, you're using something else, just find the tool. It will be there, and you can run your complexity checks. And this logically leads on to the idea of complexity pipelines or continuous integration pipelines. So basically, you can attach tools like PHPMD to GitHub Actions or Travis or Circle CI, same with ESLint, and you can set a threshold. So basically, when a developer submits some code, they push the code up, they will run the checks in GitHub Actions and tell you whether you've breached the thresholds, so that it will stop developers writing code that's too complex. You can have a threshold, and it can be a really useful way to keep complexity under control on a very basic level. So you can make sure methods don't go over a 5 or a 10, and you keep some complexity under control. Obviously, that doesn't, just using metrics and tools doesn't present a perfect solution or a complete solution to this problem, right? For keeping complexity under control. You have to start understanding code design or thinking about code design and start writing code in a certain way or analyzing code in a certain way to look for how complexity creeps into your code or where it might begin emerging in your code. So I'm just going to give a quick example, right? So in this very simple function, we have a simple method that checks for children who are above 5 feet tall. This might be a method that exists in some sort of theme park system. So like, for instance, you can only get a ticket if, or the child can only have a ticket for the ride if they're above 5 feet tall. Now, this code, if you ran this against a cyclomatic complexity check, would only get a score of 4. We've got the method signature, we've then got 2 for each control structures, and we've got an if statement. So we get a score of 4, which is pretty good, right? It's not too complex. And if this was standalone code, if this was some sort of tiny microservice existing in its own, and you're working in a small team, this probably isn't a problem. It's relatively simple code. You can read it, you know what's going on. You're looping over some parents, you're getting their children, and then you're looping over those children and checking which ones are above 5 feet tall, and then you're returning that array of children. Really simple. The problem with this code comes in at the fact when you begin to test it, because essentially what you've done here is, with this code, you've nested your business logic inside 2 for each loops. And what this means is that when you test this code, you have to spin up a world where a bunch of parents exist and a bunch of children objects exist, when in fact, all you really care about is this business logic, which is doing the feet conversion. So you're converting from centimeters to feet in this case. So that's a bit of business logic that would need to be tested, right? But you don't want to have to create all these parents and children every time you want to just test that line of code. And the same with the check to check that the child's over 5 feet, right? Ideally, like, you'd want to abstract this code into its own like little methods, and then you can test those methods robustly, right? Away from the sort of orchestration code, which is the for each loops. So you've got to be careful and you've got to think about this. So when you're doing, like, looking at code, you've got to think, can it be made simpler? Can it be abstracted a little? And can we get at the raw business logic and just test that? Because that will minimize our complexity and give us a bit more confidence. And this leads us on to the subject of code isolation, right? And code isolation is a concept that underlines clean architecture, if you've heard of that, and partly to do with domain-driven design, but that's a bit slightly more tenuous link. But mainly it deals with clean architecture. The issue with clean architecture sometimes is it's not done at a lot of companies because it's quite a big concept and it requires a lot of buy-in. And ultimately, you have to understand the underlying idea, which is this idea of isolation. So we're going to look at that briefly and explain it. But in very basic terms, code isolation deals with separating things out into their component parts. And there are a couple of basic principles to this. So the first principle is A should not know about B or C or anything else. And then the second principle is if A uses B, it should not know where B came from or where B is going. Now, in real terms, what this means is something like this. Business logic should not know about databases or file systems or anything else. If business logic uses data, it should not know where data came from or where data is going. And the basic idea here is that you're isolating your business and domain logic away from things like I/O, away from input/output. So stuff that calls file systems or calls databases, business logic should not know or care about that stuff. It should just be dealing with raw data, really, or data objects. So there's a caveat to this, right? Which I'm going to touch on before I go into a code example. Code isolation is a concept based around the idea of abstraction, but it is different, and it doesn't necessarily align perfectly with the concepts of wet and dry code. For those who haven't heard of what wet and dry are, wet stands for write everything twice, and dry stands for do not repeat yourself. And these are nice practical dev ideas to do reasonable code. So basically, you try and keep code dry. So you try not to write the same code multiple times, right? Because that in itself can add complexity, right? Because if you need to make a change, you will have to make it in multiple areas. The idea of wet is similar to dry, but less extreme. Basically, it's saying you can write everything twice, like you shouldn't basically abstract until you've got a good reason to abstract and dry up code, until you've written everything twice, more than twice, okay? But don't confuse this with abstracting to achieve isolation, right? Because you can abstract to achieve dry code or wet code as such, but not achieve isolation. And the next code example will try and highlight this. So in this code example, we have a little bit of JavaScript. It's actually Deno, which I've been playing with a lot, but basically TypeScript as such, I think. And what we're doing here is we've got three methods. And they go and get some post data from the famous place JSONplaceholder.com, and they then manipulate that data. And this is not well isolated code because we're going away and we're dealing with I/O. We're going to the internet and fetching some data, and then we're retrieving it, and then we're manipulating it in the same place. And doing that makes coding difficult, testing difficult, because you're going to have to mock stuff, and you don't necessarily need to if you want to test how you manipulate data. And this code is in breach of the dry principle and the wet principle, because we've basically got the fetch method called 3 times in 3 different methods. So it's neither complying with wet nor complying with dry. We've written it 3 times, right? So in theory, a developer might come along and go, I'm going to tidy this code up. And they would do something possibly like this. So they've abstracted the fetching of the data, the call to JSON placeholder, into a single method called fetch posts. And then they've used that method in the other 3 methods. Now, essentially what we've done is we've complied with the dry principle and the wet principle. So we made it dry when it was wet, or when it was in breach of wet. But what we haven't done here is we haven't actually isolated our code. Our call to the IO, our call to the internet to go and get some data, is still in the same place that our data manipulation or data mapping functionality, our business logic, sits. They still sit in the same method. So we haven't got nicely isolated logic. So I hope this clarifies this idea that wet and dry principles are useful, but they don't necessarily lead to well isolated code. So now we're going to briefly jump into a code isolation example. So I'm going to show you some of my code. Hopefully I can pull the code up nice and quick. And yeah, I'll just wait for it to come through. So I think you should be able to see that code now. And basically what we have is 2 examples I'm going to show you. And again, they're TypeScript, they're Deno, but I know this was meant to be, this is PHP North East, but it doesn't really matter. It's all about the principles. It's not necessarily about the code. It's how the principles work of code isolation and complexity, rather than what language you're using. Now, in this first example, we have what I would classify as coupled code or non-isolated code. Again, where basically our call to IO, our call to input-output, exists in the same place to our business logic. And this code is relatively simple. What we have is we have some people data, which looks like this. So we have a file, some JSON, and it's got a bunch of people in it. And we're going to manipulate this data. We're going to retrieve it and we're going to manipulate it. So in our first example, we have a method called adults. So as it suggests, what we're going to do is we're going to go and retrieve the data, and then we're going to loop through it and return the adults only from the data. And as you can see, we go and get the data from the file, we turn it, we pass the JSON, and then we filter these people dependent on whether their age is greater or equal to 18, so that they're an adult. So we return the adults from the list. Now that again is relatively simple. It's not going to really trigger any complexity flags if you've got them running. So in theory, what's wrong? And then below we've got a second method. This time is doing children. It's doing exactly the same thing. It's going away and it's going to get the people data. It's going to parse it, and then it's going to loop through it and check this time whether the person's age is below 18. And if it is, it's going to return the children, basically. Now, this code is super simple, not doing anything particularly complicated. And again, if it was just like a microservice existing in isolation on the internet, and it wasn't doing much, and it had a few basic like integration tests, it would probably be fine, no problem. The issue you get though is if you take this approach to coding and apply it across a large project, across numerous microservices, or across a vast monolith, you're going to begin to hit problems really quickly, because testing is going to become really, really hard, and your complexity is going to become really difficult, and you're not going to be able to reuse any code. So the question comes, like, how could we tidy this code up a bit and make it a bit more isolated so it becomes a bit more usable, easier to test, and more composable, and we pull out these business logic areas into their own place. So we have a more isolated system, and I've broken this up into two areas. And this isn't perfect, but we've got our domain is broken down into the file system and down into essentially what you might call our people model, or just our people domain. And we've got more files, so in theory, maybe this is more complex, but each file and each part is simpler and easier to use. We basically have what we could describe as an orchestration layer, right? Now this is one of the blurry areas where no theory holds perfectly tight. You can't completely isolate code. You're going to have to do some form of orchestration that brings I/O and business logic together. That can't be avoided. But you can make this process easier, right? And the point being that if you separate out your business logic, that can be robustly tested on its own in isolation. So in this orchestration module, basically, we go and get our data. So we read our JSON, and then we pass the resulting data to a very simple transformer. So what this does is this takes the data, which is in an unknown state, a raw state, and turns it into a collection of people. And this adds a layer of robustness to our code, right? So we know that we've now got a collection of people. We've taken this raw data, we've parsed it, we've made sure we've got a collection of people, which makes the objects more usable, right? And if we go back to our main module, once we then have that people collection, we can then filter it. And we can filter it against a very simple method, which is adult. And if we have a look at our helper, we have a simple method for isAdult. All it does is it consumes a person, checks its age is greater or equal to 18. And this is a significant benefit to us because we've basically abstracted this code entirely, and we've used some interfaces to do that, right? So we've given our code a bit more structure. So we now have this concept of a person, and we have a collection of persons, which is a type of people, right? So if we flick back to our helper module, we've got this very simple method. We can then test this, and we can test this really robustly. So we can write a whole array of tests. So we can create this concept of this person called Joe. We can pass in Joe to our isAdult check and make sure that they are an adult. Their age is 18, they are an adult, true. And then as we can also then check false, so we can check that Sandra, who is only 15, that they are not an adult, and returns false. And what we've got here is suddenly we've isolated our business logic, and we can test that, and we can ensure that this code works thoroughly. And this is particularly important when you've got vastly complex systems, right? Because observability becomes more difficult in more complex systems. You lose that sort of natural observability, whereby the project is small, the team is small, and people understand the domain well. In vast systems with vast teams, or big teams at least, probably over 10 or 20, observability becomes more difficult, and you have to put faith and trust in code a bit more, and testing a bit more. So the easier it is to test this stuff, the more robust it is, and the more you'll have a handle on complexity. And it also just makes it easier for us to add features, right? So again, as you saw in the helper module, we also have our isChild method. And again, it's super simple. It takes in this concept of a person object, and then it does a check against the age, and it will return true or false. And this code follows the earlier principles, right? So it takes in a person. It doesn't know where that person came from. It could have come from the file system, as it does in this code, or it could have come from the internet, or it could have come from somewhere else, who knows? And it returns a Boolean. It doesn't know where that Boolean's going. It's just going to return a Boolean, and it knows nothing more. It is happy in isolation as such. Okay? And then once we've done this, we've created this separation, it becomes much easier to compose new code. And this isn't perfectly composable code with, you know, higher level functions, but the principle becomes quite clear. You can quite easily copy this, and we can write some code. We can create a children method. We can again go get our people. We can transform our people, and then we can do something like this is charm, right? And we'll just import that. And suddenly we now have our children code. And this code just looks so much simpler than the previous example, right? It's easy to understand. And each part of it, while there are more files, are easier to understand. It's simpler code. It's more robust code, and it's more testable code. And if you're working on big projects, this is the sort of thing you need to be thinking about, because this will keep complexity under control. You'll always have some complexity, but this will keep it under control. So let's leave the example. I hope that has sort of given you a good idea of what I'm getting at with this code, and we will jump back to our PowerPoint. So there are a couple of final points on this topic of complexity before I open up to questions, and because it is a very big subject, and it's not just about the code you write. One of the main parts of development is planning, right? And planning doesn't mean you know, you're planning, you've got a 6 or 12-month plan in mind, because that's almost impossible in software development. You can barely plan a month ahead. But what it means is that you start thinking about the code that you've got to write, say, in the next sprint, and you start planning and thinking about some of the edge cases, some of the examples, and you get ahead of the complexity. Planning helps you get ahead of complexity and understand some of the known unknowns, and maybe pick out some of the unknown unknowns before you write code, right? The more you plan ahead of writing the actual code, and the more you talk about coding and the code you've got to write, and more about the domain, like through things like example mapping, the less complex the problem you will face when you actually come to write code. If you've worked at places, and there are quite a few places that work like this, that basically don't do much planning, and then they make the developer do the discoverability as they write the code, that drives up complexity, drives it through the roof, and you get bad subpar results as a result. So when you're thinking about handling complexity, think about planning and doing some, you know, example mapping, or just talking about the problem you need to solve in the domain you're dealing with before you start writing the code, because it will put you in a better place. And then the last thing to talk about is documentation. Documentation is really important for handling complexity. Basically, the more documentation you produce, and obviously you have to keep documentation up to date, right? So like, it has to become part of your coding process. But like things like readmes, code comments can really, really help with complexity, right? Because a lot of complexity and a lot of intent of code can be hidden in the code. It can't be clear why code is doing something in a particular domain, in a particular use case. So code comments, for instance, can help reveal that. And a well-placed, well-thought-through code comment can undo a huge amount of complexity that, you know, can confuse a developer. So definitely be looking at code comments. They can help you with complexity a lot. And then readmes and wikis and things like that, if you can keep them up to date and you can write them, when you've got developers starting on projects, it can just help them get going so much quicker. and it can reduce the complexity of a system, particularly in large systems where complexity, you've got natural complexity, you've already got a lot of complexity. So do think about documentation. It's not just about purely the code you write. Things like planning and documentation do help. So that's the end of the talk. I hope it was useful, but I hope the takeaway from this is complexity can be handled. It can't be avoided. There will always be some level of complexity, but you can minimize it, and you can minimize it by using metrics, by analyzing your code properly, by running good CI pipelines, by isolating your code, and by planning, by doing a bit of thinking up front about the code before you write the code, and then by writing some documentation. That's the talk. I hope it was useful. I hope it's helpful. If there are any questions on YouTube, I will try to answer them now. Thank you. So I think there is a question from Rob Howdell, which is, does code refactoring assist in reducing complexity or not always? So I think obviously refactoring code will help solve or reduce complexity, but I would say as I touched on with the wet and dry principles, you've got to be careful how you refactor your code. And I would say you've always got to be thinking about the isolation, particularly around your business logic. If you can isolate business logic, that will help a lot. But also looking at your metrics, like if you're not running any complexity metrics on your code and not looking at them and not assessing them, and you find if you go back to a code base tomorrow and you run some complexity checks and you see that you've got a few methods with some bad scores, obviously, like if you can just begin to reduce those complexity scores and do it incrementally. Say, for instance, you set your highest method is a 50, which is very high. You could start with like setting a complexity threshold of 45 and fixing the code so everything is below 45. Then you could reduce it down to 30, and you can incrementally reduce it. Yes, refactoring code will help, but obviously think about it and come up with a strategy that works for your team and your situation. So I will wait a couple of more minutes if there are any talks, but if not, is there any more questions? Okay, so there is another question from Chris on mocking and dealing with I/O. So yeah, that's a very good question, and obviously, you know, you can't escape the reality that you're going to have to at some point deal with input-output. So you're going to have to deal with a file system and a database or the internet, whatever, right? You're not going to have a very good application if it exists in perfect isolation from anything that's useful, right? So you're going to have to do some mocking, right? But this is the point, right? If you've isolated your code and you've isolated the business logic, the decision making, from your IO code, from your input output, you're going to do less mocking, right? And mocking is the thing that makes testing difficult. And lots of people complain about tests being difficult, right? And they say, oh, I don't like testing because it's difficult, right? Testing isn't difficult. Usually what's wrong is just the code is poor. It's like poorly structured, poorly designed. And that's what makes testing difficult. It's not that tests are some sort of inherently difficult. It's often that there's, you're testing poor code. So if you isolate your code, you can reduce the amount of mocking you do. I would always believe mocking is probably better than running away and actually interacting with a file system. And it helps, obviously, if you've got well interfaced code with good contracts, and you've got transformers in to build collections and things, that does help a lot. But obviously, that does raise the question of then like actual solid integration and end-to-end tests. It's not an area that I'm an expert on, but obviously when you're doing testing, you've got to do the full gamut, everything from unit testing through integration, end-to-end, and probably some QA as well to make sure your code and your application actually work. Okay, I think I am going to leave the talk there as there don't seem to be any more questions, and I'm going to hand back over to the guys at PHP North East. Thank you so much for listening, and thank you for the many kind comments.
Hey, so thanks for that, Rob. It was a really interesting talk. There's a lot to reflect on there. And thanks again to our sponsors, Ronald, James, and Iron Property. Have a good evening, everyone.